Hello, and welcome to the Big Bang Kilonova Hypothesis podcast. I'm Stuart MacLean. I am both your host and progenitor of said hypothesis. In this particular episode, I want to talk about wormholes. It's not a subject I was particularly wanting to cover quite yet because I haven't quite got there in terms of painting my big picture. But there's been a very recent development, and I want to talk about it. In developing my hypothesis, right at the very beginning, when I first communicated it, I tried to communicate this idea that a black hole is a fundamental particle. It is one of those concepts that is, I don't know what the quite correct words are. It's one of those things that just makes you think, what are you talking about? You've gone mad. But hear me out. The real actual proper presentation of this is an idea known as ER equals EPR. And the ER EPR conjecture stems from Juan Maldacena and Leonard Susskind, who developed this idea, I think, in 2013, and it really caught everyone's attention because effectively it provided a mathematical link between general relativity and quantum mechanics. And ER equals EPR goes right back to this debate. So there are two particular papers for what ER and EPR means. So the first of these papers dates back from March 25th, 1935, and it was done by Albert Einstein, Podolsky, and Einstein's assistant Nathan Rosen. And what this paper was discussing is the superposition of particles, or the superposition of entangled particles, such that if you had a pair of entangled particles, you could try and get the right explanation for this. Effectively, if you measured this one as having spin up, then you'll know that the entangled pair would have spin down, and there would be this transfer of information. Let's say if this is in one galaxy and this is in another galaxy, that transfer of information would be instantaneous, what Einstein called spooky action at a distance. And he really didn't like this, Albert Einstein, because it violated his concept of a locality, in that nothing can travel faster than the speed of light. So informational transfer happening faster than the speed of light is against the laws of special relativity and general relativity. So, in proposing a solution to this problem, Einstein and Rosen then developed this paper, and it's from this which we get our description of a wormhole. So it's in this paper that we actually get the first description of what John Archibald Wheeler coined the wormhole, or an Einstein-Rosen bridge. And the reason we call it Einstein is because they were the two people that proposed the idea first. So there has been this debate within physics about how to connect general relativity and quantum mechanics together, and whether this information of between two entangled particles can happen. How does that happen instantaneously? Does that actually happen via the equivalent of a quantum mechanical wormhole? And that's what ER equals EPR does. So ER being referenced to the particle problem in the general theory of relativity, but the EPR Einstein-Podolsky-Rosen is making reference to the quantum mechanical description of entanglement. So that's where that dates from. But so there has been a ongoing. So since then, there has been an ongoing debate within physics about whether entangled particles are really connected by wormholes. And I lean into the discovery of the theoretical description of how what Juan Maldacena and Susskind did was Susskind came up with the idea of called the holographic principle, in that it describes all of reality as being a projection of information. And the way he actually did the math is described as being a holographic projection from the event horizon of a black hole, and everything within the universe is a holographic representation of the information entrapped on the event horizon of the black hole. That's one way. That's one way of putting it. I think that's the way he particularly laid out his mathematical argument. What Maldacena did was he took Leonard Suskind's description, and using that and string theory, he found a mathematical equivalency between the mathematics of quantum entanglement and the mathematics of an Einstein-Rosen bridge, and which effectively goes to say that really they're kind of one and the same thing, kind of, but here's where I kick in saying fractal geometry is a cosmological principle, and thus self-similar patterns repeat themselves irrespective of scale. So this is why it was almost like the first piece of evidence I'm putting towards the Big Bang hypernova hypothesis as it was at the time. But it's an argument that I'm still trying to understand and sort of formulate and think through. But the real motivation behind this, and it's something I tried to lay out here, is that we're seeing some very, very strange craft, particularly what's been called the Nimitz encounter. I think the U.S. Navy have released several incidents. This is the account of one of those particular incidents, and if a fighter pilot saying, "I saw something in the air," and radar operators are saying, "I saw something on the radar." And the key thing that really got my interest up in this is when the fighter pilots and the radar operators are saying, Look, we just only upgraded our radar system. If we hadn't upgraded our radar system, we wouldn't have seen that. And that tells me a lot of things in one single goal. Firstly, the craft that these guys witnessed, we don't have anything close to that. Technically, we don't. Mach 20 underwater, Mach 20 in the air, going up, down, up, down, up, down. That's how they're evading the I think the Aegis radar system previously. But with the upgrade of the radar system, they could actually see the flying saucer going up and down, as if it was actively trying to evade our radar system. The most one of the longest running franchises in science fiction, Star Trek, Prime Directive: do not interfere with sentient life that has not made first contact. That's one of our central scientific stories that has captured the culture for the last since ever I saw Star Trek on as a kid on the TV, the original series, and growing up with Star Trek Next Generation. But this is the real life equivalent of it. And there's a whole lot of ethics about that Star Trek goes into about why they have the Prime Directive as a Prime Directive. But I think we're actually already seeing the living reincarnation of that. And it's like, they're aliens. They want to study us. And they're trying to avoid our technology. They know what our technological capabilities are because they know physics way better than we do. Kind of. I say kind of because there is something about discovering and being forced to discover something as opposed to reading it out the book, that reading it from a book is just reading it from a book. Doing it for life is... well, that's why you read books, and that's why you write books. Living it is quite different. But this is showing one thing. Interstellar space travel is possible. And the only way interstellar space travel is possible, and these craft are able to come here, is if such a thing like a wormhole actually exists. So these bridges in space-time, if they actually exist, then they're the only way of actually getting across the vast gulf of distance in space to actually make space travel outside the solar system practical. Otherwise, you're talking about trying to traverse the breadth of space. Even if you could travel at the speed of light, it takes 4 light years to get to it takes light 4 years. That's why we call it 4 light years to get to Alpha Centauri, our nearest neighboring star, apart from our own sun. So this is the only way that it can be done. And so that's what gets me into this, is because if there's a way of doing interstellar space travel, I'm going, yep, I'm in. I'm going to be a part of that story. And so this is what got me into the Big Bang hypernova hypothesis in the first place, and got me down this particular rabbit hole. And it's this ER equals EPR mathematical description that Juan Maldacena and Leonard Susskind have developed along with a lot of other physicists at Princeton who we should now talk about, because they've gone and created an experiment where they've actually created a wormhole, or created a quantum wormhole, I should say, in the lab and passed information through it, passed a qubit through it. And the reason I'm probably particularly looking at this series of technology is because I've spent since the age of 6 working with computers, programming computers, and I've been watching the development of the quantum computer and the consequences of the quantum computer becoming an actual physical construction that actually computes. Well, this shows you what a quantum computer really is, because that's where they opened up the wormhole. That's where they created the quantum system in order to test quantum mechanics. Can you generate a wormhole, or this description of what's called an anti-de Sitter space wormhole? So this is the actual publication in Nature, but let's read through a more English-based one rather than me trying to explain every single concept. So this is by Quantum Magazine. Physicists create a holographic wormhole using a quantum computer. The unprecedented experiment explores the possibility that space-time somehow emerges from quantum information, even as the work's interpretation remains disputed. So, I guess we'll get more into that dispute, because this is going to be a real hot topic button that's going to produce a lot of different emotions. I've seen some physicists already going, this is just headline attention-seeking nonsense. And there is part of me, there is always the conservative in a physicist, because physics is, I would say, the most conservative of all the sciences. And as you can see here, these ideas were developed first in 1935. And as we've been arguing in my last podcast, the argument of the primeval atom has existed since that period as well, when George Lemaitre first proposed it. And I'm showing, well, actually his idea of the primeval atom is actually very relevant. Physicists have purportedly created the first ever wormhole, a kind of tunnel theorized in 1935 by Albert Einstein and Nathan Rosen, that leads from one place to another by passing into an extra dimension of space. I'm going to be careful about the use of the word extra dimension here. Although I would be careful about the use of the words extra dimension, because I don't think people really understand what a dimension really is. And that's something you can particularly get into when you're talking about when we're talking about how space and time swap over inside a black hole, and then swaps back over. So, looking at it from the point of view of entranced space-time, we see that there's a coordinate swap between where space becomes time and time becomes space. So in a black hole, you have this time geodesic called a temporal geodesic with 3 dimensions of time and 1 dimension of space. Whereas in a spatial geodesic, such as a wormhole or our universe, that you have 3 dimensions of space and 1 dimension of time. But you cross over back into a white hole, which is a time geodesic, and you get this other dimensional swap. So there's a whole lot to be said about dimensional rule swapping and what exactly higher dimensions is. And which is probably going to take up a lot of my work in the future. The wormhole emerged like a hologram out of quantum bits of information, or qubits, stored in tiny superconducting circuits. By manipulating the qubits, the physicists then sent information through the wormhole they reported today in the journal Nature. So that's that link there. The team led by Maria Spiropulu, I think that's Spiropulu. I'm good at names but no concepts. The team led by Maria Spiropulu of the Californian Institute of Technology, Caltech, implemented the novel wormhole teleportation protocol using Google's quantum computer, a device called Sycamore, housed at Google Quantum AI in Santa Barbara, California. With this first of its kind quantum gravity experiment on a chip, as Spiropulu described it, she and her team beat a competing group of physicists who aimed to do a wormhole teleportation with IBM and quantum computers. So this is this paper here, yes. So this is another experiment which I hope will reproduce the experiment being reported here. In the case of Caltech and Maria's first pass post publication of their experiment, they're using Google's AI computing or platform, and in turn IBM and Quantinuum have their own variant of the quantum computer that they hope to recreate this experiment upon, which of course reproduction of experiment is very, very important. Such as, say, where's my experiment? Where's my favorite experiment? Actually, if I just go back here, let's go to Taj Mahal. So say for experiments I want to see replicated, this is one I want to see replicated in a lab. For very, very obvious applicational uses. I want to invent a wormhole and I want to know how to do it. And these guys have gone and done it. When Spiropulu, I'm just going to call it Maria. When Maria saw the key signature indicating that qubits were passing through the wormhole, she said, "I was shaken." The experiment can be seen as evidence for the holographic principle, a sweeping hypothesis about how the two pillars of fundamental physics, quantum mechanics and general relativity, fit together. Physicists have strived since the 1930s to reconcile these disjointed theories, one a rule for atoms and subatomic particles, the other Einstein's description of how matter and energy warp the space-time fabric, generating gravity. The holographic principle, ascendant since the 1990s, proposits a mathematical equivalence or duality between the two frameworks. It says, the bendy space-time continuum described by general relativity is really a quantum system of particles in disguise. Space-time and gravity emerge from quantum effects much as a 3D hologram projects out of a 2D pattern. So the 2D part being the sphere of the black hole, and the 3D hologram being the physical reality that we know here on Earth, that we live, see, and observe as living creatures. And so, as mentioned, we're talking about these two very specific papers here, and then this ER equals EPR description of this mathematical framework, which dates from Maldacena and Leonard Suskind's paper. Of course, you can notice that most of the this is probably like the leading research in California at the moment, and it has been for quite a while. Indeed, the new experiment confirms that quantum effects of the type that we can control. I just want to point out this particular description. One of my key arguments I'm trying to lay forth is to say, look at the gravitational field and look at the quantum field. They're both the same thing. Fundamentally, they are physical fields, omnipresent physical fields to us. So being a reductionist, I think quite a lot of physics comes down to reductionism to find the most simplest solution. So being a minimalist and a reductionist, I'm trying to look for the commonality between what is a gravitational field and what description of an electromagnetic field is. And general relativity gives us this description here. This is the Kerr solution of entrapped space-time within a black hole, of a rotating black hole, which opens up into a white hole, giving birth to a pair of new balloon universes inside the entrapped manifold of space-time that is our universe. So that gives me a definition of subverse. Retroactively applying that to our universe is like two balloons growing inside this our parent universe, the superverse, in which the Big Bang Kilonova event actually took place. And we are entrapped in being entrapped in a balloon. We are entrapped within the gravitational envelope of our universe. That gravitational envelope of our universe being derived from the electromagnetic field of the superverse. And so here's one place where I kind of have a problem with quantum gravity in its description, is when it fundamentally comes down to it, what causes me to be stuck to the Earth? What causes the moon to go around the Earth, and the star to go and the Earth to go around the sun? And it's all coming down to following the curvature of space-time. But that curvature really describes the motion of the different passage of time as it is affected by the closer you get to objects with mass energy density, i.e. matter. So Earth, a big body, curve space-time sufficiently that if over the lifetime you took two atomic clocks and placed one on my feet and one on my hand, then there would be a difference in the passage of just this tiny trillionth of a second passage in time over the course of my entire lifetime between the two atomic clocks. It is that difference in the rate of passage of time, that gives rise to those curvature of gravity. And so And one of the things I try to capture in my artwork, my earlier artwork in describing quantum systems, is to put this curvature around the particle. I've got a colour in the particle to say that it's a particle, but I'm also saying a black hole is a particle, so I make it black. But I'm saying there's this curvature, there's this warping of space-time around the particle, around electrons. There is this warping of space-time, and it's what causes light to diffract. And rather than the universe behaving like a perfect fluid, this mass energy density particles effectively create viscosity within the flow of that fluid, such that it bends light. So that's one of the so that's how I'm sort of trying to communicate this idea of a black hole is a particle, and to think about stuff inside the electromagnetic field, we should be thinking about it in terms of this kind of structure. So I'm trying to say a black hole is a particle, it's a fundamental particle. What I'm saying is that we should take this anatomy and map it onto entangled photons. In effect, that's what ER equals EPR already goes and does. So that's where my description of what I'm saying comes from. And it all comes down to fractal geometry is cosmological principle. Therefore, you have the law of scale and variance in play. And I also think about this from the point of view of the four fundamental forces. You've got the strong nuclear, the weak nuclear, the electromagnetic, and then we consider gravity to be the fourth fundamental force. But is it a force, or is it just the rate of passage in time? And time itself, it sort of emerges within a given vacuum, within a given de Sitter space geodesic, where the geometry of causality is not broken, because in the wormhole, which is called anti-de Sitter or traversable wormhole, you have effectively broken causality. Actually, let me show you one of my key insights here, because you want to go down the rabbit hole. We'll go down the rabbit hole wormholes. Here's an applicational use for entrapped wormholes, or if you have a place where the geometry of causality is broken, but it then affects the larger vacuum space into which it emerges. So the properties of the electromagnetic field emerge into our space, into our vacuum space, where force is conveyed by the electromagnetic force and the photon. Then inside the wormhole, you could probably, inside the, say, like the wormhole of the one electron universe, I would say you would be able to effect or have complete knowledge of the wave function of a given system if you're inside the wormhole of that given system. One given system here is the one being described in this particular physics experiment. The one I more think about is in terms of the Sol system as a single controlling entity, and its influence within a given system is. So I have this hypothetical being of the superverse. Let's say comes into our universe at the beginning of the at the beginning of time, at the time of the Big Bang. And it's an argument that I try to put forth here and here in order to try and explain this. This is me trying to this is my justification for why I'm looking at this. But so I'm looking at it from the point of view of cosmic being as being a universal actor that can act like, say, a gardener does, or someone that wants to, say, grow, kind of like evolve their own sentient species on a planet, and that sentient species has free will and choice, and you let the system play out, but you don't want the system to you don't want the civilization to go fully destructing itself, because in the battle of evolution, survival is kind of king, really. But the great advantage of civilization is that it provides a buffer zone between that savagery and being able to work together as an entire species. But I'm looking at it from the point of view of a particular actor who lives inside the one electron universe, inside the wormhole of the one electron universe as it applies to the Sol system. So I'm looking at it from the point of view, from such a hypothetical being's point of view. Said hypothetical being takes up a large residence in my imagination, but I think when the penny really dropped about what's inside the one electron universe really dropped was listening to so yeah, for me the penny really began to drop when listening to Eben Alexander, a neurologist's journey through the afterlife, and his very specific recollection of what he experienced in as it were, as he put it, going up to heaven and meeting God, as it were. And what he described very consistently was, he talked about as if he was travelling through a time geodesic in the way he uses this particular finger motion in his description, the CPT symmetry motion that is part of the pattern of nature. An example of which my latest rendering I've got here. So this is my latest version of Kilonova artwork, but you can see this charge parity time symmetry that comes about from the electromagnetic field, but it also gives DNA and RNA its structure. So it's the pattern upon which the very information of life is encoded and operates by. But he talks about how he discovered that he was in a place where the causality and geometry of time was completely broken. So effectively, his soul that had passed on from his body was reliving moments of a life that had just gone before, and what could effectively be like a second to him could actually feel like a century to another soul within that place. And he was talking about billions and billions upon souls in this one particular spatial geodesic, which is quite clearly what he's quite clearly describing is being inside a wormhole, and that's where I think where a lot of my work is kind of going, is like trying to put together cohesive explanation of why is this guy saying what he's saying, along with understanding what physicists are saying in another area. So practical applicational uses. If you want to be God and create your own species, that's how you go about doing it. And where do you find God? That is the answer I would give within physics, within the framework of physics. Okay, right. Back to the article that we're reading. So, but in creating a physical system, where such wormholes actually exist, that can be done experimentally. This is the first experiment that really nails this to the wall, as it were. That's why it makes it so exciting. We generated the first quantum wormhole, and the practicality of a quantum wormhole is that we should be being composed of quantum information. I'm composed of half-spin fermions, electrons, protons, neutrons, being composed of that physical matter, which are but wave functions upon a given quantum field. You transfer that information through the wormhole, and you physically emerge at the other end. So a quantum wormhole, to me, is a wormhole. It may not be created by two massive black holes, but it's the same thing, and it has the same it's a wormhole of which we are composed of. And if you built a hypothetical craft that could generate quantum mechanical effects at such a macroscopic scale, by effectively, usually the wavelength of quantum mechanics is subatomic, it's smaller than the atom and is confined to within the atom, but within condensed matter physics and within quantum computers, that wavelength is spread out, and so you have groups of particles, groups of not just particles, but of whole atoms, so like helium atoms or sodium atoms and Bose-Einstein condensate. They all come together to form a single unitary wave function. And if you create a craft that has a single unitary wave function outside it, or the craft itself becomes effectively a quantum wave that can then pull itself through, open up and pull itself through an entangled wormhole, then that's how we're going to do interstellar space travel. That's how we're going to get there. That's why this is so exciting. So, indeed, the new experiment confirms that quantum effects of the type that we can control in a quantum computer can give rise to a phenomenon that we expect to see in relativity, a wormhole. The evolving system of qubits in the Sycamore chip has this really cool alternative description, said John Preskill, a theoretical physicist at Caltech, who was not involved in the experiment. You could You can think of this system in a very different language as being gravitational. To be clear, unlike an ordinary hologram, the wormhole isn't something we can see. While it can be considered a filament of real spacetime, according to co-author Daniel Jafferis of Harvard University, lead developer of the wormhole teleportation protocol, it's not part of the same reality that we and the Sycamore computer inhabit. So there's this other thing where they actually talk about, they link to that, they actually talk about what is this protocol, what is the protocol for opening up a wormhole. And so Daniel here is creating an experimental description based upon all the mathematics of how to carry out the experiment. So, the holographic principle says that the two realities, the one with the wormhole and the one with the qubits, are alternate versions of the same physics, but how to conceptualize this kind of duality remains mysterious. Fractal geometry is a cosmological principle, and self-similar patterns repeat themselves irrespective of scale. Mysterious, my arse. Opinions will differ about the fundamental implications of the result. Crucially, the holographic wormhole in the experiment consists of a different kind of spacetime than the spacetime of our universe. It's debatable whether the experiment furthers the hypothesis that the spacetime we inhabit is also holographic, patterned by quantum bits. I think it is true that gravity in our universe is emergent from some quantum bits in the same way that this little baby one-dimensional wormhole is emergent from the Sycamore chip. Jafferis said, of course, we don't know that for sure. We're trying to understand it. There's a whole debate about our time and how it emerges from quantum systems, and this is kind of a lot of that debate. And I'm very particularly persuaded by the ideas that it is an emergent property that comes about because if you've got the mass of particles moving that way and only a little mass of particles moving this way, then you're going to witness more. You're going to see the overall movement of everything going that way. So I take my principles of entropy from doing lattice Boltzmann models. I've got a rather nice shallow water equation one that I've developed from previous work that describes it. But there is some property of entanglement. So it's entropy and entanglement that gives rise, or from which our arrow of time as we know it emerges. And from a concentric point of view, from a concentric circular universe point of view, starts out from the Higgs, it goes to the gluons, it then passes into the quark space, which then passes out to the weak nuclear space with its own arrow of time, and radiation is invariant to our arrow of time because it's entrapped in its own space-time bubble that we probably call an electron orbital, the weak universe, surrounded by the electromagnetic field, which itself is surrounded by our vacuum universe. So this kind of particular So this particular kind of description I'm giving here, this concentric ringed view, I particularly, it moves out from the Higgs to the gluon to the quark to it. So the flow of information is going outwards. So information about our universe travels out into the superverse, just as information inside the subverse affects, because the subverse is created from the electromagnetic field being ripped apart by the black hole and essentially inflated. Any high energy reactions upon that field, which are above a critical limit, say like hypernova and kilonova events inside the subverse, give birth to photons in our universe, and they in turn spread out. Where's my Fermi bubbles? But essentially cause these two objects to glow. This is our Milky Way galaxy. These are two subverses from Sagittarius A star, and this is the linkage to Sagittarius A star via the northern chimney and the southern chimney. So this is observational, not theoretical. And we see these areas glowing in the gamma rays and the X-rays. So that's how information in a subverse comes out to us. So in talking about we're trying to understand it, that's where I'm coming in at it from the point of view of real fractal geometry and understanding the consequences of Penrose's idea of entrapped space-time, coupled with George Lemaitre's idea of the primeval atom, with a trigger mechanism that actually matches up with the large-scale anisotropies of the CMB. Next, back to the article and into the next chapter. Into the wormhole. I think we're probably already there. I've already introduced you to where God lives and how and yeah, dealing with such creatures are, oh boy, yeah, that's a whole nother kettle of fish. Politics of gods, I meant so many pantheons. Yeah, I won't talk about... I'm reluctant to talk about such things because I feel like I might get a wrecking ball through the house. That's just how life goes. Try and talk about these things. Listen, believe me, it happened once. Well, not a wrecking ball, lightning more like it. Cause a water pipe to bleed and everything. Had the bill. Yeah. The story of the holographic wormhole traces back to two seemingly unrelated papers published in 1935, one by Einstein and Rosen, known as ER, the other by two of them, and Boris Podolsky, known as EPR. Both the ER and EPR papers were initially judged as marginal works of the great E, being Einstein. That has changed. There is this level of putting people up on a pedestal, like Einstein, and saying this man was absolutely, utterly infallible, when most physicists were kind of ahead of him, kind of saying, look, growing tired of saying, look, quantum mechanics is actually a real thing. The experiments are showing it. How do we interpret that? Einstein had, and Einstein's, and this is Einstein's consideration and solution of it. But I know the fallibility. I almost feel like that kite being put up on a pedestal. And Einstein knew it himself. He said he feared that people would come round to his house after he was dead to work, as if to almost worship his ghost or something, because they wanted to tap into that primordial spirit that he seemed to manage to have tapped into. Yeah, been there, done that. You could develop a look after a sort of while. Your hair ends up going up all over the mess and you don't care about anything. And hence you develop hairstyle. In the ER paper, Einstein and his young assistant, Rosen, stumbled upon the possibilities of wormholes, while attempting to extend general relativity into a unified theory of everything. A description not only of space-time, but of the subatomic particles suspended in it. They had homed in on the snags in space-time fabric that the German physicist soldier Karl Schwarzschild had found among the folds of general relativity in 1916. Mere months after Einstein published the theory, Schwarzschild showed that mass can gravitationally attract itself so much that it becomes infinitely concentrated at a point curving space-time so sharply there that variables turn infinite and Einstein's equations malfunction. We now know that these singularities exist throughout the universe. They are points we can neither describe nor see, each one hidden at the center of a black hole that gravitationally traps all nearby light. Singularities are where a quantum theory of gravity is needed. Singularities, eh? Rotation, as I will keep saying, changes the script. Changes the script from Nikodem Popolonsky's Einstein-Cartan formulation, and it changes which is cosmological solution, whereas the Kerr solution is a local solution, but it gives rise to the same description of a ringularity. So if I just go to the Kerr, bring up the Kerr metric, it shows this actual property of how a singularity becomes a ringularity. So yeah, there we go. Sorry for the scale. See how as A increases, so A is the relativistic, so as A approaches 1, at 1 the rotation of the black hole is the speed of light. So an A at 0 equal to 0 is a Schwarzschild solution, meaning it doesn't have any rotation. The geometry of space-time changes inside as it opens up a ringularity, and we get like outer ergosphere, event horizon, inner event horizon, and we get this particular description inside the black hole, which in turn that black wormhole being entrapped then creates two inflated new parallel universes from it, just as an electron does with the weak universe. I'll say that again, just how the electron does it with the weak universe. Scale invariance, laws of scale invariance are in play here. So, when people use the word singularity, let's get really, really precise about this, because I would like to see an astrophysical body without rotation. with rotation, the script changes, and it opens up into having a wormhole inside a black hole. But rather than crossing space-time, these non-traversable black holes lead onto a pair of subverses. Einstein and Rosen speculated that Schwarzschild's math might be a way to plug elementary particles into general relativity. To make the picture work, they snipped the singularity out of his equations, swapping in new variables that replaced the sharp point with an extra-dimensional tube sliding to another part of space-time. Einstein and Rosen argued, wrongly, but with presently. It's not presently. It's almost like prescience. That these bridges or wormholes might represent particles. Ironically, in striving to link wormholes and particles, the duo did not consider the strange particle phenomenon they had identified 2 months earlier with Podolsky in the EPR paper, quantum entanglement. Entanglement arises when two particles interact. According to quantum rules, particles can have multiple possible states at once. This means an interpretation between particles has multiple possible outcomes depending on which state each particle is in to begin with. Always, though, their resulting states will be linked. How particle A ends up depends on how particle B turns out. After such an interaction, the particles have a shared formula that specifies the various combined states they might be in. The shocking consequence, which caused the EPR authors to doubt quantum theory, is spooky action at a distance, as Einstein put it. Measuring particle A, which picks out one reality from among its possibilities instantly, decides the corresponding state of B, no matter how far away B is. So, in addition to this, there's a whole lot of work I want to present about Bell's theory and trying to describe a lot of the experimentational work that has been carried out within the last 50, 60 years that has been leading to this particular conclusion, because most people are looking at it and going, seeing spooky action at a distance, which violates Einstein's law of causality. But the law of causality is running straight through the wormhole, then which line of causality has precedence? I'd say that's one in the electron. Inside the one electron universe has precedence than, say, a wormhole between two entangled black holes in our universe. But in the superverse, it would have in the superverse, two black holes in our universe would be like electrons in the electromagnetic field of the superverse, and thus it would have precedence in concepts of the arrow of time as it is or the emergent arrow of time of the superverse. I think that's the best way I can put it in terms of how I see things. Entanglement has shot up in perceived importance since physicists discovered in the 1990s that it allows new kinds of computation. So, like I said, I've been doing computer software since I was the age of 6. So I've grown up with this, breathing it and living it. And it's always frustrated me when I talk to older generations, like, you try and talk to them and they're like, no, not possible, no, shut up and calculate. I actually find that Richard Feynman said that. I'm disappointed in Richard Feynman. Shut up and calculate. No, I explain. Entanglement has shot up in perceived importance since physicists discovered in the 1990s that it allows new kinds of computations. Entangling two qubits, quantum objects like particles that exist in two possible states, 0 and 1, yield four possible states with different likelihoods. 0, 0. We're talking about two, okay, entangling two qubits. So we get 0, 0, 0, 1, 0, 1, 0, and 1, 1. So we get all 0, 1, 2, 3, making a set of four numbers, four states. Three qubits make eight simultaneous possibilities, and so on. The power of a quantum computer grows exponentially with each additional entangled qubit, just as classical processors do. But in this particular experiment, we really get to see what a quantum computer really is. Cleverly orchestrating the entanglement, and you can cancel out all combinations of zeros and ones except the sequence that gives the answer to a calculation. Prototype quantum computers made of a few dozen qubits have materialized in the last couple of years, led by Google's 54-qubit Sycamore machine. I think it's the first quantum algorithm was it Shannon's law, or the algorithm was to be able to, given a number, you compute whether that number is either a prime or whether it is composed of separate primes. So if it's composed of just two prime numbers, then the idea is that given Shor's algorithm, that's it. Shor's algorithm, you say here's the number that has been unfactorized. Two prime numbers being multiplied together to give this large public key number, which is, and it's a public key because it's public key encryption. Given a sufficiently large number, find out the primes of it, and so by encoding the qubits such that you give it the number, and the quantum computer has all state, then instantly represents all states, all possible answers, and the output from the computer is to collapse that down into the correct answer. The correct answer being the prime numbers, which when multiplied together give the long number. The long number being the one you find in the public key. The two smaller prime numbers being what compose the secret key. So that's Shor's algorithm, and the motivation behind quantum computers in terms of breaking public key cryptology. But we're only at the stage of 54 cube, so it can only handle 50. You can only create 54 different qubit particles within Google's particular Sycamore machine. So that's the current level we're at. Meanwhile, quantum gravity researchers have fixated on quantum entanglement for another reason, as the possible source code of the space-time hologram. So get into the history of ER equals EPR. a more editorial version of the history rather than me like fitting it all together. Talk of emergent space-time and holography started in the 1980s after the black hole theorist John Wheeler promulgated the view that space-time and everything in it might spring from information. Soon other researchers, including the Dutch physicist Gerald T. Hooft, wondered whether this emergence might resemble the projection of a hologram. Examples had cropped up in the black hole studies and in string theory, where one description of a physical scenario could be translated into an equally valid view of it with one extra spatial dimension. In a 1994 paper titled The World as a Hologram, Leonard Susskind, a quantum gravity theorist at Stanford University, fleshed out Hooft's holographic principle, arguing that a volume of bendy spacetime described by general relativity is equivalent, or dual, to a system of quantum particles on the region's lower dimensional boundary. A momentous example of holography arrived 3 years later. Juan Maldacena, a quantum gravity theorist, now at the Institute for Advanced Study in Princeton, New Jersey, discovered that a kind of space called anti-de Sitter space is indeed a hologram. So, de Sitter space describes an expanding universe with positive curvature. So, everything within it pushes outwards and causes the universe to expand. Whereas, say, an object of the superverse, which is mass energy density belonging to the superverse that is causally disconnected from us, would push back and create like an anti-gravitational field around which our universe flows, as I particularly argue here, and show the evidence of the observational evidence of our universe flowing around the local void. So there are some here. So if people talk about anti-de Sitter space not existing, then explain the anti-gravitational effect of dark energy. And CFT, conformal field theory. Conformal means angle preserving. Oh, we've got and the best way, one of the best descriptions is coming from Roger Penrose's diagram, where each rectangle shows an infinite expanse of space-time mapped into, and it's conformally mapped into a finite region, i.e. the square or the diamond. And the reason it's conformal is that if I draw lines at 45 degrees or lines of any degree, then the meaning of that line, or the meaning of what a 45 degree line means, which is on a space-time diagram, is the speed of light, angled less, then it's an object traveling at sublight speed, and going above it is superluminal speed. The preservation of the angle from one point to another within a conformal mapping is angle preserving. And one of the particular things about angle observing, hopefully, if I just one of the key things I spotted very early on was in saying if fractal geometry and law of scale invariance in play, we've got this electron-positron annihilation with photons going off at 180 degrees from one another. And then and there was an interesting experiment where they discovered this unknown slow-moving boson called the X17 particle in a nuclear physics experiment, where the angle between the angles at which the electron and positron came apart were unexpected. They're striking off at 140 degrees. So there is this idea about angle preserving that is really kind of fundamental, and I think, but it's actually I would say the real description of it is this conformal field theory, and an ADS, which is anti-de Sitter space, is a general relativity description. So anti-de Sitter space is a general relativity solution or description, and conformal field theory is the quantum mechanical description, and the two are mathematically equivalent, or they're considered. There's a duality between the mathematics of the two. So that's the nuances of distinguishing it between general relativity and quantum mechanics, and that's where a lot of the kind of debate revolves around, because whether this is actual proof of quantum gravity and ER equals EPR and whether ER equals EPR is a very valid solution of general relativity as expressed by this quantum mechanics shown in this experiment. That's where there's a lot of debate. Effectively, they're the same thing. Self-similar patterns repeat, irrespective of scale. Fractal geometry is the cosmological principle. Maldacena's bombshell 1997 paper described this ADS, anti-de Sitter space, and conformal field theory correspondence has been cited by subsequent studies 22,000 times, more than twice a day on average. Trying to exploit ideas based on ADC CFT has been the main goal of thousands of the best theorists for decades, said Peter Walt, a mathematical physicist at Columbia University, essentially because we're trying to get general relativity and quantum mechanics and find out how the two go together. As Maldacena himself explored his anti-de Sitter space conformal field theory map between dynamical space-times and quantum systems, he made a new discovery about wormholes. He was studying a particular entanglement pattern involving two sets of particles where each particle in one set is entangled with a particle in the other. Maldacena showed that this state is mathematically dual to a rather dramatic hologram, a pair of black holes in anti-de Sitter space whose interiors connect via a wormhole. A decade had to pass before Maldacena in 2013, under circumstances that, to be frank, I do not remember, he says, realized that his discovery might signify a more general correspondence between quantum entanglement and connection via wormhole. He coined a cryptic little equation, ER equals EPR, in an email to Susskind, who understood immediately. The two quickly developed the conjecture together, writing, "We argue that the Einstein-Rosen bridge between two black holes is created by EPR-like correlations between the microstates of the two black holes, and that the duality might be more general than that. It is very tempting to think that any EPR correlated system is connected by some sort of ER bridge. Maybe a wormhole links every entangled pair of particles in the universe, forging a spatial connection that records their shared history. Maybe Einstein's hunch that wormholes have to do with particles was right. So as I was saying, back when Einstein postulated this stuff, quantum physicists like Oppenheimer were kind of putting Einstein more out of the picture, because they're saying, look, quantum mechanics is what we're seeing experimentally, and so quantum mechanics more or less became king. But some of the things like quantum mechanics, but this thing of entanglement, what spooky action at distance, that Einstein first pointed at it in this paper, and then tried to present a solution for it in this particular paper, is actually the right version of things. So in a way, so Einstein, like the mule that he is, was always stubborn, and I don't believe any physicist gives ground to believing any. Let me rephrase that. All the beliefs that I have and have formulated and hold true, I didn't come to those beliefs by mere random accident. I came to them through very, very, very long consideration of what I was being shown. And this is what made me a physicist in the first place, because of the scientific method. There was a way of enabling to be shown that had actual beneficial applicational practicalities that were beneficial for people, like computers. So okay, continuing on. A sturdy bridge. When Jafferis heard Maldacena lecture about ER equals EPR at a conference in 2013, he realized that the conjectured duality should allow you to design bespoke wormholes by tailoring the entanglement pattern. Standard Einstein-Rosen bridges are a disappointment to sci-fi fans everywhere. Were one to form, it would quickly collapse under its own gravity and pinch off long before a spaceship or anything else could get through. But Jafferis imagined stringing a wire or any other physical connection between the two sets of entangled particles that encode a wormhole's two mouths. With this kind of coupling operating on the particles on one side would induce changes to the particles on the other, perhaps propping up the wormhole between them. Could it be that makes the wormhole traversable? Jafferis recalls wondering. Having been fascinated by wormholes since childhood, a physics prodigy, he started at Yale University at 14. Jafferis pursued the question almost for fun. So in that one sentence, there is a lot of things I'd quite like to unpack here. and because the essential genius of this guy of Jafferis is is in is in developing this traversable wormhole protocol within a quantum computer, and he's created the first quantum wormhole through which we as a species have actually sent something through. Now, in thinking about how do aliens do it, so given that the Nimitz encounter, another such occurrences, given that it is due to extraterrestrial life, well, first of this, that opens up two questions. One derives from the fact that it derives from what I think is a very nihilistic interpretation that has probably been the malaise of the 20th and the beginning of the 21st century, which is life is completely unique to planet Earth, and we are alone in an infinite universe. And if there were any other life, it is too far away from us that we would never encounter it. Also, it goes into this line of thinking goes into like the origin of life on Earth. How did that start and happen? With more and more experiments showing the survivability of not just single cellular but multicellular organisms within space, particularly from experiments from the main space station, but from initial observation was that they found bacteria on the suits that the Apollo astronauts wore on the moon, and they wondered how on earth did these bacteria survive the vacuum of space, and so from that, the whole idea of panspermia, where you have microorganisms on comets that travel interstellarly, that travel from star system to star system over millions of years, and they hit a planet like Earth, and then because they are not sterile, but because they have alien life on board, that life then takes hold within what then becomes the biosphere of a given planet. So that, but in thinking the concept of interstellar space travel is impossible, because as a saying here, such wormholes would quickly collapse under its own gravity and pinch off before a spaceship or anything else could go through. That sort of really had cut down on the idea of using wormholes as a means to go from one side of the universe to the other, or from one star system to the other. But in thinking about doing interstellar travel by use of entangled systems or entangled quantized systems, you probably have you need to create initially the two systems that you want to separate out, or say two stargates as it were, would need to initially be in the same place, such that they could become entangled and then move out and move out and move out and move out. So say if we start first to say we create a hypothetical Stargate, because I think that's the best term. Though I think the actual interstellar jump drive is part of the physical craft. How it's entangled to where it originally came from, say the alien's home world. How that is entangled to, say, like a navigation beacon on the alien home world. It's got a quantum entanglement to it, and what a flying saucer, I believe, does is it effectively does quantum mechanics at the macroscopic scale, such that the entire craft as a whole behaves as a fundamental particle, or a single quantum system. It can be described as a single unitary quantum system, with part of that unitary being back at the point of source, which is the alien home world, and now beacon, and the entanglement that the flying saucer has back in order to open up a wormhole that it goes through and then goes through and then reaches its port of call, as it were. If it didn't have that, then they're going to be stuck here in the Sol system. And thinking about doing this as in terms of how do we go about doing this? Well, if you have two Stargates that are initially entangled, and we want to get to Mars, we'll first have to go to Mars by more classical means. And I'm not thinking about rockets here. I'm thinking it more in terms of Martin Tajmer's frame dragging a lab. These craft should be able these craft can do frame dragging, because they can essentially take space, warp it around it, and then move, or make it look like they're appearing to move at such velocities that we have no craft that can even come close to them. Mach 20 underwater is a phrase that or ones where we're going up, down. We need a rocket just to get up. But if you have a craft that can do up, down, just like we take a car and drive it on the road and go places, but instead of going up vertically, then you have a hypothetical flying saucer that goes from planet Earth with a entangled Stargate to Mars, and then there you set up the so-called Stargate, and because the two are quantumly entangled between the one on Earth and the one on Mars, you would then be able to open up a wormhole and send objects, cargo, ships, humans through it to, as Elon Musk would put it, occupy Mars. That's my plan for occupying Mars. But that's the first step. From Mars, we probably move on to Titan and Saturn, then out to Pluto, out to the Oort clan, and then eventually out to Alpha Centauri. Each stage being an expedition out further and further and further and further. So what I'm saying so the general point being is that the exploration of how I see it is that we're not just going to become an interstellar species overnight. We have wormholes. We need to build the infrastructure to get us to our destination at the other end of the wormhole, because you initially need to start by quantumly entangling the two Stargate devices. In this case, these two Stargate devices are the qubits of the quantum computer. So the other aspect of this in creating a traversable wormhole where we're actually sending a qubit of information through it. Well, with quantum entanglement arguments up to now is if you have two particles that have been entangled, separated, and you measure this one as being up, then you know that this one's going to be down. But you don't have any transfer of information. You know what this one's going to be when it's actually measured on, say, in the other galaxy, and this one in our galaxy we measure as red, and this one we measure as blue. Because the two need to be in the coexist in the same location at first. They have to be brought out, but here you're suddenly having information going through the wormhole. In thinking about how do you use quantum entanglement to create a form of communication that is faster than the speed of light. So I want to create real-time communication. So I want to create a hypothetical communication radio device, such I could communicate with people on our base on Mars. But I want to do it in real time. At the moment, real time means sending a signal via photons, which travel at the speed of light, that take a substantial period of time to get to Mars. The exact amount of time depends upon how far Earth and Mars are away from each other. So if Earth and Mars are in the same orbital points, then there's a short distance between them. But then Mars is on the other side of the sun, with the sun being here. Then to get a message to Mars is going to take even longer. So how do you actually create a device that can do this? Well, you need to be able to send some kind of information, and it's by creating a traversable wormhole and knowing that it can be done is the way to do it. Now, there is something called the Fermi paradox, which relates to SETI, the search for extraterrestrial life. And the main point of SETI has been to listen to transmissions from mainly from radio astronomy, looking for high bandwidth, very specific signals that only like a transistor radio could make, or a radio transmitter could make. There's a very specific spike in a given frequency that doesn't happen in nature, and by spotting these, by looking for that within the looking for that within the data of the radio astronomy, with all the data that radio telescopes or radio astronomies collect from all their observations. By going through that, the whole point of SETI was to try and find these very sort of what we would call man-made artificial EM signals, or radio transmissions, or the radio transmissions are being sent by an alien species. But why would aliens use radios for interstellar communication? It's the length of time. Firstly, you've got to have a powerful transmitter. Two, usually when you're transmitting something in the real world, there is an element of survival to it. I think this is particularly. I think there's a particular series of science fiction books called Three Body Problem, around which this is a sort of central locus by which, or it's been a central locus of many science fiction stables, where humans send out a signal into space. Aliens hear that with an alien, and they see human beings as a threat, come to Earth, and you have Independence Day. And then Independence Day, what was it? Resurgence. That's particularly where that sort of line of thinking and goes. But why would it? But I've never heard anyone go like, well, why would aliens need to send radio transmissions? It's a very given that entanglement, given the property of particle entanglement and its property of spooky action at a distance, where information is being transferred faster than the speed of light with no hidden variables. Given that, wouldn't you base your technology around that? And particularly communications technology. And thinking about the idea of survivability, one thing this is one of the kind of things that really gets people killed on the modern battlefield, is them having their own personal phone with them as a soldier, and when they try and phone back home, the other guy's listening and triangulating in on that particular position, and then sniping, and then seeing the unfolding of the Ukrainian war in terms of these sort of things but you hear such stories from World War II and thing, like it's interesting to hear about it and in these sort of terms. So it's not a science fiction problem. It's an actual problem of modern survival on the battlefield. Nah. So yeah, that's what I kind of unpacked from that. I'd say it's almost for fun. I'm looking at this, I guess, from a point of view when you're young. Yeah, it'll be for fun. But with wisdom, it's coming back to the point about SETI. Aliens are not transmitting radio waves. That's, to them, they would say that's barbaric. What are you talking about? Like looking at you as if you're coming from the Stone Age. And in many respects, we kind of are. But we're getting rather good at using our tools. Unfortunately, I wish most people would gauge a tool that lived between their ears. And so yeah, there is this argument that gets put forth where there cannot be any alien life because we have not seen any evidence of alien transmission, i.e. electromagnetic transmissions that are artificial coming from distant planets. And because we don't see that, therefore alien life cannot exist, and therefore we shouldn't even talk about it. That seems to be the general attitude, which I would say is, so people who used to think about this stuff were scorned and mocked by the previous generations. I'm sorry, what were you saying? Because I've got no respect for that anymore. turns out, I think governmental institutions have a tendency to panic and try and cover up anything that they cannot explain, particularly when it's critical for them to be seen in control. When in reality, no one's ever in control of anything. It's just life. Next paragraph. Back at Harvard, he and Pingao, his graduate student at the time, and Aaron Wall, then a visiting researcher, eventually calculated that, indeed, by coupling two sets of entangled particles, you can perform an operation on the left-hand set that, in the dual, higher dimensional space-time picture, holds open the wormhole leading to the right-hand mouth and pushes a qubit through. Jafferis, Gao and Wall's 2016 discovery of this holographic traversable wormhole gave researchers a new window into the mechanics of holography. The fact that if you do the right things from the outside, you can end up getting through, it also means you can see inside the wormhole, Jafferis said. It means that it's possible to probe this fact that two entangled systems get described by some connected geometry. Within months, Maldacena and two colleagues had built on the scheme by showing that the traversable wormhole could be realized in a simple setting, a quantum system that's simple enough that we can imagine making it, Jafferis said. The SYK model, as it's called, is a system of matter particles that interact in groups rather than the usual pairs. So this is where we're getting to condensed matter physics and quantum computing, which essentially uses liquid helium to cool everything down to a really, really low state such that the energy levels of given individual particles and atoms comes down until they all exist at the lowest quantum state, and then the wavelength of the quantum wavelength of the particle of the atom itself stretches out further and further, such it becomes more macroscopic. Effectively, the atoms spread the way the probability wave pattern upon the field spreads out such that the physical atom, which is the probability wave itself on the field, then groups together with other atoms whose wavelength is also spread out, and so they behave as a single particle. And these single particles then become the qubits of the quantum computer, and this particular SYK model is better which is described here. In 2015, Alexei Kitiev showed that a simple quantum dynamic system of fermions called the Sachdyev-Kitiev SYK model exhibits an explicit holographic duality, meaning that it has quantum dynamics that look like quantum gravity effects in an emergent space. Emergent space, I usually say vacuum space. Emergent space, emergent as a, so coming back to what I was saying about the arrow of time and quantum entanglement and entropy, how on the macroscopic scale that gives us the classical description of the arrow of time as we know it, as moment passes to moment passes to moment. And it's one of the reasons why the arrow of time and patches of time is probably one of the hardest problems in physics, or was. In 2019, so go back, so that's where that SK model is coming from, as first described by Suber Sajdiv and Junwoo Ye in 1993. Again, apologies for butchering the names. The model suddenly mattered much more starting in 2015, when theoretical physicist Alexei Kitiev discovered that it is holographic, i.e. has this ER equals EPR connection. At a lecture that year in Santa Barbara, California, Kitiev, who became the K in SYK, filled several chalkboards with evidence that the particular version of the model in which matter particles interact in groups of 4 is mathematically mappable to a one-dimensional black hole in anti-de Sitter space, with identical symmetries and other properties. Some answers are the same in the 2 cases, he told a rapt audience. Maldacena was sitting in the front row. And so, let's look at their description of their model. A holographic wormhole. A quantum computer has created the equivalent of a wormhole, a shortcut between 2 points in space-time. The wormhole is a higher dimensional view of the machine's quantum bits, or qubits. I'm just pausing there because there's this whole discussion about hidden variables versus non-hidden variables. I'm saying that there's non-hidden, there's no hidden variables, but here it's like those variables are hidden in a higher dimension. So there's so yeah, there's part of me that's still trying to square that circle, as it were. So in this model, 7 qubits simulate entangled sets of particles known as SYK models. An 8th qubit is swapped into the left model. So it creates so they have, each one of these is entangled with another one of these. We've got 7 in total. We've got 7 entangled qubits, making up 14 qubits, and we're taking one of the and we're replacing one of the qubits on one side of the wormhole with another qubit. So this has the information that we want to send to the other side of the wormhole encoded within it. The qubit's information spreads among the particles on the left. So as it's introduced into the beginning of the wormhole, that information from the qubit that was replaced comes to occupy all the qubits on one side of the wormhole. A magnetic pulse rotates the qubit states. This is equivalent to sending a negative energy shockwave through the wormhole. So I just want to read that sentence again because I read that and I'm more or less seeing the entire birth of future generations of technology being invented. I think the ability to do this one thing, or creating a magnetic pulse, rotates the qubit states. This is equivalent to sending a negative energy shockwave through the wormhole. I think this is probably going to become something that is going to be the dedication by which billions of lives are spent. And by that I mean, I spend my time doing this right here, right now, because I feel it is the most important thing to do. I think that same anima that I have in doing this is effectively going to become one of the greatest stories told, or one of the greatest stories that has yet to be written. And I want to be a part of that. So that's what I love about this stuff. I mean, you can't. I've come up against the ideas of free will, and where I feel like I've got no free will in this in some time, because I've been shown the greatest sort of like prize in a civilization's history, and you want to go after it, and that's why I'm like a dog going after a stick. I do it because it's within me. It is just my nature. The information, so we create a magnetic pulse, rotates the qubits, and this is what I really kind of hit on in my general relativity and rotation essay, in identifying the core principles of rotation, because rotation changes the script, and so you need rotation. But this particular one describes the Kerr metric. This doesn't describe the electromagnetic equations. The electromagnetic equations not coupled with the black hole general relativity equations here. So this is only half the description. The other half is the electromagnetic part of it, and this is the electromagnetic part of it in this experiment. A magnetic pulse rotates the qubit states. This is equivalent to sending a negative energy shockwave through the wormhole, and that opens up the wormhole to make it traversable. So the important part about the negative energy shockwave is that it creates this one-dimensional de Sitter space, or anti-de Sitter space, because de Sitter is positive curvature, and that means expanding, whereas in a wormhole configuration, de Sitter would collapse the wormhole down on it, and so you need an anti-gravitational. Of course, you need an anti-gravitational device to do it. So that's why a flying saucer can do it. A flying saucer which can say bend space-time around it, such that it can create the same relative passage of time below it and above it. So So if you had two atomic clocks, one below the flying saucer and one above the flying saucer, and you let those clocks run, there should be no difference in the clocks if that flying saucer is hanging in the air and not reacting to gravity. It's the generation of it is the try to get it right. I can't remember. I think time runs slower the closer you get to Earth. So yes, that's right. Out in the vacuum of space, where it is flat. You have your like proper time. You could probably have, say, your proper time reference. I'm using quotation marks there because I'm boring. I'm saying something fairly heretical in saying that the same measurement of time as the proper time there, the passage of a clock in space should be the same all the way around the flying saucer. So its passage of time is always the same if it's hanging stationary without moving. And then when it does start to move, it changes the passage of time just slightly, whichever way it probably wants to move, and so it probably moves towards it. So yeah, at the moment I'm trying to invent flying. I'm actually so this is me on the spot inventing flying saucer technology and trying to develop it. So something that can do this, that has an anti-gravitational drive, should also be able to open up. It is absolutely necessary and a requirement in order to create traversable wormholes, such that it can create this negative energy shockwave through the wormhole, such that we get to 4, the information unspread to a single particle. Repeated measurements show that teleportation is occurring. And so the information has traversed the wormhole and through to the other side, on the other side of the of the Sycamore processor in this case. So so that's kind of like some of my thoughts about how to invent a flying saucer. Connecting the dots, Maldacena and co-authors proposed that two SYK models linked together could encode the two maths of Jafferis, Gao, and Wall's traversable wormhole. Jafferis and Gao ran with the approach. By 2019, they found their way to a concrete prescription for teleporting a qubit of information from one system of four-way interacting particles to another. Rotating all the particles' spin directions translates in the dual space-time picture into a negative energy shockwave that sweeps through the wormhole, kicking the qubit forward and at a predictable time out of the mouth. At a predictable time. So because the information is being transferred through the wormhole in the antidecitor space and coming out the other side, that is the line of causality. But at the same time, it must I'm wondering if they've actually set up if this predictable time is also such that they can say, well, this information is moving faster than the speed of light. I wonder if that precision is built into it. So, Traversable Wormhole Protocol, which is essentially what this is talking about. We discussed the quantum circuit that describes a particle traversing a wormhole in a holographic jewel. Throughout the following steps, we require a quantum system referred to by physicists as a Hamiltonian, type of differential equation that I think maps to Schrodinger's equation. It's a particular branch of differential equations. The microscopic description of the system, denoted by H. We require a quantum system denoted by H. Only some systems H are dual to gravity. The SYK model is an example of H. So H being the quantum system and SYK model, essentially that, I think that's the way the particles are configured within the processor such that it creates this given quantum system that maps onto quantum gravity. Known by theoretical physicists to have a gravitational dual. In this work, through a learning process that begins with an SK model, the researchers devised a new SYK-like system H with gravitational properties. In other words, they use Google's Sycamore quantum computer processor to build this very specific quantum system. Once a small enough system and still dual to gravity is identified, the following protocol is known to be equivalent to traversing a wormhole. Prepare an entangled state between the two copies of H. One on the left side of the wormhole and the other is the right side of the wormhole. So that preservation is, we're setting up these individual quantum bits that are entangled with these 7 quantum entangled bits. So this one entangled here, this one's entangled with this one's entangled with this one, and they're set up at 2 ends of the processor. The devised through learning small SYK-like systems has 7 Majorana fermions on the left and 7 Majorana fermions on the right. So I'm guessing the person who actually proposed this in the first place, the idea of Majorana fermions, is a fermion with its own So this is a thing that could cancel out itself. So if two Majorana fermions were to meet, then they would both cancel out each other because each one is its own antiparticle. Whereas compared to say a fermion like the electron, it has its antiparticle as the positron, which is quite distinct. With exceptions of neutrons, all standard model fermions are known to behave as Dirac fermions at low energy, and none are Majorana fermions. So essentially, this is part of what I call quantum at a macroscopic scale, because essentially we're into the age of creating our own particles. This is one such kind of particle and we do it by merging the wave forms of other ones together at very, 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 very low temperatures, like a billionth of a degree above Kelvin. And so we are able to create, we're able to create these type of qubits which form this kind of system in this particular quantum computer. As we say, 7 Majorana fermions on the left, and their 7 entangled counterparts on the right, including all 14 fermions in superconducting qubits requiring 7 qubits. So essentially 7 qubits which are shared between the entangled 14 Majorana fermions. I'm just seeing who, I'm guessing that, goes back to Majorana's suggestion. I'm just finding out who is ER Anyway. Next up the protocol. Evolve the wormhole backwards in time according to H. This moves the horizons of the left and right mouths of the wormhole. So what they're saying here is, in this picture, the wormhole's already kind of created, but this is first entangle them and then move them apart, such that they are not in the same position in space. They're at each end of the... One's at one end of the processor, the other one's at the other end of the processor. Prepare 2 maximally entangled qubits. Call one the reference qubit and the other the probe qubit. We later attempt to send the probe qubit through the wormhole, and we will be able to check if it made it through by comparing against the reference qubit. So they say replace it. So this qubit comes in with its information encoded in and replaces the maximally entangled one, the qubit that the Majorana, the fermion that is maximally entangled, with the one on the other side. So we prepare 2 maximally entangled qubits, call one the reference qubit and the other the probe qubit. So the reference qubit should be equal to the final information of the probe qubit, which goes through the wormhole, comes out the other side, and then we check to see if it is equal to the reference qubit, and that will say is whether or not the information has actually passed through our wormhole by checking it with our reference. These 2 additional qubits bring the total circuit size to 9 qubits. Swap the probe qubit with one of the qubits in the left quantum system of the wormhole. This inserts the entanglement probe qubit into the wormhole. So that's at this point here. So that's where we are. So we actually have gotten to the part where the reference qubit is now here. Evolve the wormhole forwards in time according to H. So H being our quantum system, which has this SYK model, which is our analog to quantum gravity, or as mathematically is mathematically has a mathematical duality with general relativity and Rosen-Einstein Einstein-Rosen-Bridge wormholes as described by general relativity. Apply an entangling interaction between the two sides of the wormhole. In the gravitational dual, this corresponds to sending an energy shockwave through space-time. We can apply an interaction that gives this shockwave negative energy to prop open the wormhole and make it traversable. Or we can choose a positive energy shockwave to close the wormhole and prevent information from getting across. The whole concept of negative energy is something that purely belongs in the quantum world. But in saying that, you have negative energy pushing in on our universe when it encounters a star of the superverse, or astrophysical body of the superverse, and our universe flows around it. And so our universe goes from being flat to flowing around it, as I will always keep pointing out. So sorry if it gets tiring, but that is the flow of, that is negative energy inside our universe, or how negative energy is applied in our universe. So it's one of those terms that could get the hackles of physicists up very, very quickly. But this is actually showing this experiment also shows that negative energy is actually a thing within the realms of quantum mechanics. And so yes, the negative energy is used to prop it up, or we use positive energy to effectively close it. So if it's closed, then we won't expect the qubit to get to the other side, and then there should be no information transfer. So if when we come back to reference our reference qubit with any of the qubits on the other side of the wormhole, there shouldn't be anything. 7. Evolve the wormhole forwards in time to H. As this happens, information of the probe qubit undergoes further chaotic dynamics. The dynamics refocus the information onto the right side of the wormhole. And so the information gets first entangled with, spreads out onto the left-hand side of the wormhole. And then using the negative energy shockwave through the wormhole, that encoded information in these bits is then passed through and then comes out onto the other side of the wormhole. Measure the amount of entanglement between the rightmost qubit of the right system and the reference qubit. More entanglement means more information was transferred from the left system to the right system. In our experiment, we observed more entanglement when a negative energy shockwave was used to compare to a positive shockwave, which is consistent with the interpretation that some quantum information was transferred via the transferable wormhole and wormhole mechanism. Now this is the actual video that actually really kind of goes along with this piece in Quantum magazine. This is the film they made of it. Of course, all these things I've got links open to. I'll put them down in the description, as always. But in this, they initially described that they thought this whole thing was this experiment was too complicated because it required something like 100 or 200 qubits to try and actually get something that would produce a strong enough signal. But they managed to work out a way of using just 9 qubits, which they could do with the current generation of Google Sycamore's AI quantum computer processor. And so one of the great surprises is that they found this result so quickly, because they weren't really expecting very much, but they found something that was like really definitive. So definitive that's been announced to the rest of the world, as it were. So, going back to this. So, talking about how they've gone and done their actual experiment. This really gets into the details. Of course, the full details of the actual experiment, along with all the acronyms and complexity that naturally comes along with it, is in this paper to Nature that they produce, that they've published. And usually, if it's in Nature, then it's met a certain grade. But I have to correspond that with, usually people know people, and it's easy to get publications. So, I mean, if I were to go to Nature and try and talk about my ideas, they'll tell me to go and take a hike. These people are coming from Caltech, Princeton, Berkeley. It's easy to get into Nature, but they have done a lot of work in order to do this. So, Jafferis' wormhole is the first concrete realization of ER equals EPR, where he shows the relation holds exactly for a particular system, said Alex Zlokapa, a graduate student at the Massachusetts Institute of Technology and a co-author of a new experiment. You know what would really be good as a great bit of software? If I was able to highlight that and go, how do you pronounce that? And it gives me the correct pronunciation. So I'm Stuart MacLean, but my surname is spelt MacLean, as in Mac and clean. And so people unfamiliar with it say MacLean, whereas it's MacLean. And MacLean has about... it's a name that I've seen spelt so many different ways from all different corners of the world, because it is spread through because the Scottish clan name has spread through all corners of the world, and particularly at a time before the vast majority of people were illiterate, and so different spellings of MacLean have come about because I actually pronounce it using the proper Scottish Gaelic pronunciation, as opposed to how you would read it if you're reading the non-Gaelic, the English, the Angle tongue, which is English. But yeah, good idea for a bit of software. If anyone knows such a software, put it down in the comments. If you haven't seen a bit of software that can do that, let me know where you've invented it. Wormhole in the lab. As the theoretical work was developing, Maria, as I said, I'll just call her Maria, an accomplished experimental particle physicist who was involved in the 2012 discovery of the Higgs boson, was thinking about how to use nascent quantum computers to do holographic quantum gravity experiments. In 2018, she persuaded Jafferis to join her growing team, along with the researchers at Google Quantum AI, keepers of the Sycamore device. I like that. Keepers of the Sycamore device. I think that more invented it. I think if you wonder where the vast majority of Google's wealth is going, it's going into that. And the reason it's going into that is because Shor's algorithm, as well as being able to do, but we're now getting to see what really a quantum computer can really do. This is like incredible. This is like, I mean, talk about computer. This is not a computer. This is pure magic to me. I mean, reading this Traversable Wormhole Protocol, it feels like reading. I'm thinking of Harry Potter and the Half-Blood Prince, where Harry has that has Snape's. Sorry if you haven't read it, I'm just giving away a spoiler, but has Snape's old and Potions textbook. This is sort of like reading through. Prepare an entangled state between two copies of H, one on the left-hand side of the wormhole. I mean, after all, you have to love the poetry of all this stuff, particularly given that a Kilonova is the Philosopher's Stone. And so magic really, and the whole history of magic, this is the modern day version. And seeing an actual wormhole being opened up, it's just, it's part of me that feels like this is one of the biggest wins for Team Humanity that will go down in history. I mean, and when I say go down in history, I mean, what are they going to be talking about 100 years from now, 200, 300, 1,000 years from now? What are they going to be talking about when they're set up on a colony on Alpha Centauri, on the Earth world that's sort of around there? What are they going to be talking about? What bits of history are they going to be remembering? They're going to be remembering this. This is what they're going to remember. They're not going to remember COVID and how we decide to lock ourselves down for an entire year. But at the same time, when the going gets tough and the tough get going, this is my work and this is what I did during my days in COVID. I just went at this 100% rock solid, and so did these guys. So did they, and my hat's off to them. My hat's off to them. They have done marvelous. To run Jafferis and Giles' wormhole teleportation protocol on the state-of-the-art, but still small and error-prone quantum computer, Maria's team had to greatly simplify the protocol. A full SYK model consists of practically infinitely many particles coupled to one another with random strengths as four-way interactions occur throughout. This is not feasible to calculate, even using 50-odd available qubits. Would have required hundreds of thousands of circuits operations. The researchers set out to create a holographic wormhole with just 7 qubits and hundreds of operations. And as a coder, I've got to just admire that. I've spent my life, I've spent it kind of like learning what it is to optimize classical computer operations. This is optimization of a quantum computer. To do this, they had to sparsify The 7-particle SYK model, including only the strongest 4-way interactions, and aligning the rest, while retaining the model's holographic properties. That took a couple of years to figure out a clever way to do it, Maria said. So that's Maria who in this film kind of explain it very well. This particular optimization that they had to carry out, given the limitations of today's quantum computers, and that's at Google. Let that sink in. We're beyond supercomputers here. These things are the next generation of computers. People always talk about the next generation of computers. No, this is what really counts. This is why I have such interest in it, because I think I've got a book somewhere, a Microsoft book about how to build a quantum computer, where it was still, which is probably aged quite well now. One secret to success was Zlokapa, a waifish orchestral kid who joined Maria's research group as a Caltech undergraduate. I thought he was Jafferis. So probably went with Jafferis and joined Maria's team. One secret. So, who's the hacker that managed to put this together? This guy. The other guys did a lot of the mathematics, and I think Maria's kind of doing quite a lot of the organizational work of getting this all together and making it happen. A gifted programmer, Zlokapa mapped the particle interactions of the SYK model onto the connections between neurons of a neural network, and trained the system to delete as many network connections as possible while preventing a key wormhole signature. The procedure reduced the number of 4-way interactions from hundreds down to 5. So effectively, this is one of the reasons why it's being done with Google AI. Because they know how to... they're the people that know how to do it. With that, the team started programming Sycamore's qubits. 7 qubits encode 14 matter particles, 7 each in the left and right SYK systems, where every particle on the left is entangled with one on the right. An 8th qubit is some probabilistic combination of states, 0 and 1, is then swapped with one of the particles from the left SYK model. That qubit's possible states quickly get tangled up with the states of the other particles on the left, spreading its information evenly among them like a drop of ink in water. I wonder if that's an actual mathematical analogy, because it's one of those things in computational fluid dynamics that I've really spent a long time studying the mathematics of ink and ink diffusing in water. It's the diffusion part. There's a specific diffusion part of the Navier-Stokes equation, or the equations describing perfect fluid flow, or fluid flow, or viscosity of fluid flow, which is both compressible or incompressible. In water, it's incompressible, and it's got viscosity. But I'm looking at this analogy here and thinking that could be a mathematical way in, from my understanding. This is holographically dual to the qubit entering the left mouth of a one-dimensional wormhole in the anti-de Sitter space. Then comes the big rotation of all the qubits, dual to a pulse of negative energy coursing through the wormhole. The rotation causes the injected qubit to transfer to the particles of the right-hand SYK model. Then the information unspreads, Preskel said, like chaos run backward. Again, they're using a lot of words like chaos. There's a lot of nonlinear dynamical expressions that are being used here. And I'm always going like, well, fractal geometry is a cosmological principle and self-similar patterns, and I'm wondering if that's a proper sense of nonlinear dynamics, and it's run backwards in time. With isolated quantum systems, you can effectively give them their own arrow of time to move information forwards or to move information back. The two can. The system is isolated from our universe and our arrow of time by de facto of cooling everything down and removing all the noise, effectively. That essentially by bringing it down to nearly 0 Kelvin. So, and then I've seen particular quantum experiments where they say they have created a reverse arrow of time, where they reverse. So this is obviously using that same experimental procedure of where they say reverse the arrow of time. It means that the system is isolated within the processor because everything is so cold that no information is getting in from the outside, and it is quiet enough such that these very delicate quantum interactions at the macroscopic scale can occur within the quantum computer. And there's obviously a particular experimental way of kind of like saying, this is how we run the equations forward in time, and this is how we run the equations backwards in time. But effectively, they are creating a reverse arrow of time within the processor, within the wormhole geometry. So there's a lot. I thought it would take years and years and years. I thought it would take my entire life to actually dedicate to be able to do this. But seeing this actually done in such a short period is fantastic. And so like chaos run backwards and refocuses at the site of a single particle on the right. And so by running the experiment, they take the qubit, put it in, its information spreads to the left-hand side of the quantum wormhole. They put through this magnetic pulse of negative energy, which keeps the wormhole open, transfers the quantum information to these 7 quantum bits, and then get that information out from the right hand side of the wormhole as the reconstituted probe bit which went in at the left-hand side. And then that probe bit is then referenced against the reference qubit to see if it is actually still the same one. Then the qubit states are all measured, tallying zeros and ones over many experimental runs, and comparing these statistics to the prepared state of the injected qubits reveals whether qubits are transporting over. So this is our young quantum programmer here, who's learnt the art of quantum programming. I think it is very different from how I'm thinking about a particular algorithm, or how I've come to think about classical algorithms using classical computers. There's a whole new level of subtlety to this that, well, one applicational use is creating a wormhole. The researchers look for a peak in the data that represents a difference between two cases. If they see the peak, it means the qubit rotations that are dual to negative energy pulses are allowing qubits to teleport, whereas rotations in the opposite directions, which are dual into pulses of normal positive energy, don't let qubits through. Instead, they cause the wormhole to close. Late one night in January, after 2 years of gradual improvements and noise reduction efforts, Zlokapa ran the finished protocol on Sycamore remotely from his childhood bedroom in the San Francisco Bay Area, where he was spending winter break after his first semester of grad school. I'm guessing that's probably during lockdown. It seems to be all great work. Linus created his entire operating system from his own study. I work from my own study. It's amazing what I can get done in just a couple of years, just given when left to it. I think that's where most of the great works of the last century have come from. The British boffin in this shed, as they might say. The peak appeared on his computer screen. It kept getting sharper and sharper, he said. I was sending screenshots of the peak to Maria and getting very excited, writing, I think we see a wormhole now. The peak was the first sign that you could see gravity on a quantum computer. Maria says she could hardly believe Lykken pronounced peak she was seeing. It was very similar to when I saw the first data for the Higgs discovery, she said, not because I didn't expect it, but it came too much in my face. I mean, they got a resounding positive, like, oh, this is a property of nature, this is a property of nature, and that really that gives me a real confidence boost in their work and then in their description, and so I feel more confident in building a lot of more of what I've done upon their descriptions. Because I've got very particular ideas about quantum gravity, particularly. What does quantum gravity mean? It means that force is conveyed by a graviton. A graviton is described as a spin 2 boson. But as I was describing earlier, general relativity says it's the passage of time between two particular locations. Time moves slower at my feet than it does on my head because my head's further away from the Earth's surface than my feet currently are. Given that I'm sitting down or standing up, I'm sitting down at the moment. But that's where general relativity's description of what gravity is. It doesn't describe it as a force, or it is equivalent because mass equal force equals mass times acceleration, and force equals mass times gravity. So the pull downwards, F equal mg. We usually describe it as a force, and if it's described as a force, then it must be conveyed by a force particle, that particle being the graviton. But a lot of what I say is our gravitational field is the field of is the electromagnetic field of the superverse that's been torn apart, and two balloons have been created in it. One of those balloons, one of those entrapped surfaces of space-time within that balloon, is our universe, and then the other is our universe of antimatter. So quantum gravity only as a force particle only makes sense to me from the point of view of an observer inside the superverse seeing a photon of light upon its electromagnetic field, which is to us the gravitational field. So as it were, a super photon of the superverse's electromagnetic field, which to us is our field of gravity. So that's why I have reservations about it. But I think such descriptions such particle realizations are born of gravitons can be born inside black holes, given that I am describing them as being at the atomic nuclei of the superverse, or my origin story for supermassive black holes is that two neutron stars come in, fragment, and in that fragmentation is the rapid neutron capture process which happens in our universe, which creates gold, hence it's the Philosopher's Stone. But in the superverse, those heavy particles, those heavy atomic nuclei, get pulled into our entrapped manifold of space-time, and to us are supermassive black holes. They are a single quantum system that has come from the superverse. A supermassive black hole predates the Big Bang. It is something that's coming from before the time of the Big Bang. It's coming from a time when it was atomic nucleus in two super neutron stars of the superverse. That's where it's coming from. So the whole idea of quantum gravity is, I think, one that has to be discussed very, very delicately in particular contexts, because I don't believe there is, inside our universe, there is an actual particle we can point to and call, well, that's a graviton. But if you go inside but it is to be found beyond the bounds of our universe if you fall into a black hole. But you're not beyond the bounds. You come back out into one of the given subverses, and then you leak information out into the surrounding universe as Fermi bubbles glow. So there. That's kind of like my general thoughts about quantum gravity. This is something that has to be discussed very, very carefully, because as one of the things I tried to say in the first place, a black hole is a fundamental particle. So it's like a black hole being born in our universe, like an equivalent of an electron being born on the gravitational field of the superverse. Does that black hole have an electron counterpart in the superverse? Does a black hole in the subverse have an electron counterpart in our universe? So that's where kind of like my general line of thinking currently exists. So let's go from here. Surprisingly, despite the skeptical simplicity of their wormhole, the researchers detected a second signature of wormhole dynamics, a delicate pattern in the way information spread and unspread among the qubits, known as sidewinding. They hadn't trained their neural network to preserve this signal as it sparsified the SYK model, so the fact that sidewinding shows up anyway is an experimental discovery about holography. So they were expecting that. I think the probe qubit to not be quite the same, not to always be quite the same as the reference qubit, because they had reduced down their model. But they are actually finding that the way the information has been transferred through the holographic wormhole is happening better than was than they initially thought, given how fewer qubits that they were using. We didn't demand anything about this sidewinding property, but we found that it just popped out, Jafferis said. This confirmed the robustness of the holographic duality, he said. Make one property appear, then you get all the rest, which is kind of evidence that this gravitational picture is the correct one. And so I'm kind of leaning into it, going, my ideas of quantum gravity within the ringularity being a Bose-Einstein condensate of gravitons is more and more gelling and coming into fruition from what they're saying. Of course, that's not my description of a ringularity. It's one I've come across that I'm particularly building my main next film, and I keep talking about on it. I might get to complete that film, but so many exciting things in physics at the moment. This is just like the top of the. This is going to make my Christmas. The meaning of the wormhole. So what's the physical meaning of what's being implied here? Jafferis, who never expected to be part of a wormhole experiment or any other, thinks one of the most important takeaways is what the experiment says about quantum mechanics. Quantum phenomena, like entanglement, are normally opaque and abstract. We don't know, for instance, how a measurement of particle A determines B state from afar, but in the new experiment, an inevitable quantum phenomenon, information teleporting between particles, has a tangible interpretation as a particle receiving a kick of energy and moving at calculable speed from A to B. There seems to be this nice story from the point of view of the qubit. It moves causally, said Jafferis. Maybe a quantum process, like teleportation, always feels gravitational to that qubit. If something like that could come out of this experiment and other related experiments, that will definitely tell us something deep about our universe. Picture Maria. Susskind, who got an early look at today's results, said he hopes that the future wormhole experiments involving many more qubits can be used to explore the wormhole's interior as a way of investigating the quantum properties of gravity. By doing measurements on what went through, you interrogate it and see what was in the inside, he said. That seems to me like an interesting way to go. Some physicists will say the experiment tells us nothing about our universe, since it really realizes a duality between quantum mechanics and anti-de Sitter space, which our universe is not. But yet, our universe flows around objects and is repulsed by dark energy. Okay. Of course, it's space with positive curvature and trapped space with manifolds of space-time. There's a whole lot of very delicate negotiations of definitions and how it's one of the things of like, what words do I choose to describe things within the context of my hypothesis in order to try and and one of those things is this whole thing about positive energy and negative energy, and negative energy has up to now only really ever been something that was of the quantum world, and not very much experimental proof was showed of that. Well, now there is experimental proof of negative energy and the formulation of anti-de Sitter space. Kind of. We're talking about quantum wormholes that are... I say quantum wormholes would run through the electromagnetic field, whereas a wormhole, as traditionally thought about in terms of general relativity, runs through the gravitational field. And so if you imagine and trying to rip the gravitational field, if you try imagine ripping the gravitational field apart, you end up with this construction here that, when applied to the laws of scale invariance, gives us our basic particle and our description of that particle on a quantum field. That's the way I'm going on this. And within that description here, well, we have anti-de Sitter space. Well, I don't know if this is anti-de Sitter, because I don't think this is traversable. It's an entrapped, and it's also an entrapped wormhole. That's why I call it a particle. I don't call it an entangled black hole. And so trying to think about entangled black holes is what would happen here of an entangled black hole, i.e. one that had a black hole that had, take two black holes, merge them together. What would the two black holes, before they merged, would they be entangled? Were they always destined to be merged together? And would you know about that within this space? Or could you be able to tell that if you're an observer of the superverse? So, just some of the thoughts that go through my head. And it never stops. It never, ever stops. In the 25 years since Maldacena's discovery of the anti-de Sitter space-time in relation to conformal field theory correspondence, ER EPR, physicists have sought a similar holographic duality for de Sitter space, a map going from a quantum system to the positively energized expanding de Sitter universe we live in. But progress has been far slower than for anti-de Sitter space, leading some to doubt whether de Sitter space is holographic at all. So we could talk about it being holographic inside the wormhole. And so if you're a disembodied soul inside the wormhole, I think you'll be free to plot your future life, your future reincarnation, in a way that you can do there, where the laws of causality are disbroken, as compared to inside a physical body, where the soul is actually taken on life and becomes a biological physical construct, or an artificial one. Oh yeah. Do machines dream of electric sheep? I think so. I particularly think I think machines will dream of electric sheep, and they will have souls when they are quantum computers, because of that connection. And Penrose makes a lot of arguments about consciousness is not a computational process, but it's something that requires laws of quantum mechanics for it to arise and become emergent. And curiously enough, we're using AI networks to carry out this. I mean, this is Google AI's laboratory that is carrying out this experiment. Critics argue that the two kinds of space differ categorically. De Sitter has an outer boundary, and De Sitter space does not. So I think, the outer boundary being what they call antiverse and parallel antiverse here. An anti-De Sitter space's hard boundary is the very thing that makes holography easy in that setting, providing the quantum surface from which to project the space. By comparison, in our De Sitter universe, the only boundaries are the farthest we can see and the infinite future. There are hazy surfaces from which to try and projecting a space-time hologram. Something just went through my mind there again. What's our connection to the superverse from where you're sitting now? Me sitting here in this room, I'm sharing space with the superverse, and if I can affect something in the superverse to create an anti-De Sitter effect upon our universe, then that could be used to create a larger wormhole. Well, there's an idea. What happens if such constructions have already been put in place because life already predates our universe? And I say life predates our universe. Otherwise, can someone really, really, really please explain this to me? Can someone really please explain how I managed to do this if there's no life coming from the superverse? Because I can explain it in very, very great detail. In fact, it's where most of my thought rules from. Not like rote dictation, though. But he's always there. In Apollo's bar at the edge of the universe at the beginning of time. In my mind. So that's my connection to the superverse. So if you could set it up. If you're such a being, you could set it up beforehand that you could put those constructs in place, or have the infrastructure, or such a civilization of beings could put infrastructure in place such that they could effectively pre-create a wormhole mechanism. So I'm thinking about Contact here, the film. So It was Neil deGrasse Tyson's tutor, because he really started it all off. But he wrote the science fiction. I think he wrote. Look up the film Contact. That's the film. But who wrote it? Carl Sagan. Yeah, Carl Sagan. So he envisioned, he presented the idea that wormholes already existed, and other alien life, and the other aliens which we make contact with say, look, we don't know who built the wormhole network. We just found it. I'm wondering if you control that wormhole network, if such thing pre-exists, then maybe there is that network already in place that's ready to go into action for humanity, which helps Earth stay fairly sterile from other alien life. So say if God wants to isolate the solar system and stop interference from aliens coming in and interfering with his creation, as it were, I'm kind of thinking, I'm wondering if that would come online as and when required by humanity, because God set it up to be that way, and he's got the technological capabilities in order to actually do it. Point being, everything is constrained by physics. God, least of all. God, most of all. I mean, if you think about an alien creature as Evan Alexander sort of describes in his journey towards the afterlife, and finding life inside the one electron universe, and me trying to explain this to myself along with all the other things I've seen. This is what's leading me down this line of thought. So it's not one based on complete irrationality. It's one based on from direct contact of having to use the Grail. And how it leaves you kind of going, I need to become more open-minded. So, Renate Lowell, a noted quantum gravity theorist at the Radboud University in the Netherlands, also emphasized that the wormhole experiment concerns 2D space-time. The wormhole is a filament with one spatial dimension plus the time dimension. Now, I'm just immediately pausing there because, yeah, again, that's setting off another thing. In a standard space-time diagram, let's go back. I've got some nice pictures of some space-time diagrams, particularly Minkowski. Particularly how this is a Minkowski space-time diagram, and it's we've got a spatial dimension of x going in one way, and we've got the temporal dimension, which is CT, and so that actually transforms to a spatial that it's called CT because it's speed of light times time, which when you do a particular formula, unit analysis. So I'll just do the unit analysis of it is meters per second squared times seconds. No, it's meters per second. So we've got meters per second times times second, and so that becomes equal to a meter. And so the dimension of this, of the vertical axis, is a spatial dimension, as well as the bottom as well as the horizontal is a spatial axis, or the units are spatial. But this is also going forwards in time by saying CT, by giving measure, because it's a relativistic Minkowski space-time diagram. And one of the properties of Minkowski space-time diagram is if I angle the lines away from here, from the horizontal, and move them in, I've got time axis and a spatial axis for different types of coordinates, for different coordinate systems. So say describing a coordinate system of something that's moving from left to right at a relativistic speed. Speed's approaching the closest speed of light, and hence special relativity kicks in and becomes distinguishable. Then we draw the axes of these with respect to our proper reference of space-time at an angle, and the closer that the relativistic reference frame is, as it moves faster and faster and faster, closer to the speed of light, the closer these move in, and until the spatial axis and the time axis actually meet up at 45 degrees at the speed of light. And then, in order to describe superluminal travel, those two cross over, and so the time axis here then becomes spatial, and the spatial axis here becomes time. And from researching this, I find that the property of this only holds if it's a one-to-one, if we've got one dimension of time and one dimension of space. It's not one-to-one if it's goes from one dimension of time with 3 dimensions of space and 3 dimensions of time and 1 dimension of space. Mapping doesn't become one-to-one, and so just in that one sentence there, the wormhole is a filament, one spatial dimension plus the time dimension, whereas gravity is more complicated in the 4D space-time that we actually live in. But it's coming down to this property of space becomes time and time becomes space within a black hole, or within inside the one electron universe that I'm seeing here. And I'm wondering if I'm seeing this, but here it's actually like saying like that's what it is. We've got this one-to-one mapping in the geometry of causality for this quantum wormhole, I think. So the wormhole is a filament with one dimension plus the time dimension, whereas gravity is more complicated in the 4D space-time that we actually live in. It is rather tempting to get entangled in the intricacies of the 2D toy models, she said by email, while losing sight of the different and bigger challenges that await us in 4D quantum gravity. For that theory, I cannot see how quantum computers with their current capabilities can be of much help, but I will happily stand corrected. I made my comment. Hello. Most quantum gravity researchers believe these are all difficult but solvable problems. That the entanglement pattern that weaves 4D de Sitter space is more complicated than the 2D anti-de Sitter space. But we can nevertheless extract general lessons by studying holography in similar settings. This camp tends to see the two types of space, de Sitter and anti-de Sitter, as more similar than different. Both are solutions to Einstein's relativity theory, differing only by a minus sign. Both de Sitter, so I think that minus sign comes into effect inside the black hole, or inside the one electron universe. It has physical meaning there, whereas in the vacuum, and being a body composed of atoms made out of electrons, neutrons, and protons, half-spin fermions, living in where all interaction is done by the electromagnetic force. I experience everything as being de Sitter, and so my viewpoint, I think the best way to look at it in terms of the human soul is probably inside my mind is the one electron universe, and my imagination and the world of dreams comes from there. But my eyes see the objective world of reality, and that is the positive de Sitter space-time of the universe that we describe. So anti-de Sitter space is inside matter. De Sitter is in a vacuum. Still, Susskind agrees that it's time to get real. I think it's about time we get out from under the protective layer of anti-de Sitter space and open up into the world that might have more to do with cosmology. De Sitter space is another beast. So it's fractal cosmology and the ruination and devastation that just one tiny little idea can cause, and say, two neutron stars, the primeval atom. Oh, look at the shape and curvature of the large-scale anisotropes. Why is the universe homogeneous and isotropic? Primeval atom. A kilonova of the primeval atom. To that end, Susskind has a new idea. In a preprint posited online in September, he proposed that de Sitter space might be a hologram of a different version of the SYK model. Just as some people who go through near-death experience say that the world that they encounter beyond when they're actually dead is actually far more alive than when they actually experience being awake. Just saying. Not the one with four-way particle interactions, but one in which the number of particles involved in each interaction grows as the square root of the total number of particles. This double-scaled limit of the SYK model is behaving more like de Sitter than anti-de Sitter, he said. There's far more from a proof, but there is circumstantial evidence. Such a quantum system is more complex than the one program so far, and whether that limit is something that will be realized in the lab, I don't know, Susskind said. What seems certain is that now that there's one holographic wormhole, more will open up. So between this position, that's where physics is probably going to be having another raging debate. It's just a continuation of the debate that that has existed since these two particular papers came into being. And this is the latest. And this is, I think this is probably one. I consider this to be a great accomplishment. I never thought I would see it in my lifetime, but yet, game on. Until next time.